Speed of light overview. The speed of light is a fundamental physical constant that represents how fast light travels in a vacuum. This has been a topic of research and debate for scientists throughout history, but it was given particular importance by the development of the theory of relativity by Albert Einstein. Initial observations. Since ancient times, people have noticed that light propagates rapidly, but the first attempts to measure the speed of light were made in the 17th century. Experiments like the one carried out by Ole Romer showed that light does not propagate instantaneously, but that it has a certain speed. Einstein and the theory of relativity. In 1905, Albert Einstein presented the theory of special relativity, which changed the way we perceive space, time, and the movement. One of the important consequences of this theory was the redefinition of the concept of the speed of light. Einstein proposed that the speed of light in a vacuum is a universal constant, and nothing can travel faster than it. Speed of light in a vacuum. The exact value of the speed of light in a vacuum is about 299,792,458 meters per second. This means that, in a vacuum, light can travel a distance of about 299,792,458 meters in 1 second. The importance of the speed of light. The discovery that the speed of light is a universal constant had a profound impact on physics and our understanding of the universe. The theory of relativity changed paradigms in physics, changing the way we think about space, time, and motion. The speed of light has implications in various fields, from communications to astronomy and advanced technology. This is an overview of the speed of light in the first stage. If you want to explore more, or let's move on to the next step, please let me know. The theory of relativity and the speed of light. In 1905, physicist Albert Einstein presented the theory of special relativity, which radically changed our perception of space, time, and motion. One of the significant innovations of this theory was the way it redefined and explained the speed of light. The principle of relativity. Einstein started from the principle of relativity, which held that the laws of physics are the same for all observers moving uniformly and without acceleration relative to each other by another. This principle undermined the idea of absolute motion and opened the way for a new understanding of motion and physics. The universal constant, the speed of light in a vacuum. A crucial discovery of the theory of relativity was the finding that the speed of light in a vacuum is a universal constant. Regardless of the source of light or the observer measuring the light, its speed remains constant and invariable at approximately 299,792,458 meters per second. Nothing goes faster than light. One of the fundamental consequences of this theory is that nothing can travel faster than light in a vacuum. The previous understanding that light was the fastest entity in the universe was now confirmed and rigorously demonstrated by the theory of relativity. Implications and revolutions in physics. The theory of special relativity opened the way to a profoundly different view of reality. It transformed the way we perceive space and time, showing that they are closely related in what is called space-time. This theory revolutionized the fields of physics, astronomy, and technology, influencing technological development and our knowledge of the universe. The speed of light in practice and variations. The speed of light in a vacuum, defined as a universal constant in the theory of special relativity, has a specific value of approximately 299,792,458 meters per second. However, there are situations where this speed may vary or impact media other than vacuum. Speed of light in other media. In media other than vacuum, such as air or water, the speed of light may be slightly less than this value due to interaction with the atoms and molecules in that environment. This phenomenon is known as refraction and is responsible for the appearance of light bending in a glass of water or optical effects in optical lenses and prisms. Results in practical applications. Modern communications, including those through optical fiber, are based on the properties of light and its speed. The fact that light can carry information at speeds close to that of light in a vacuum has led to the development of optical technology and a revolution in the way we transmit and process data. The expansion of the universe and variations in observations. Another aspect where the speed of light plays a role crucial is in astronomical observations of distant galaxies. Due to the expansion of the universe, light from distant objects can be affected by this expansion and redshift towards the red part of the electromagnetic spectrum. This has helped astronomers understand the expansion of the universe and estimate distances in the cosmos, absorption and scattering effects in certain media. Light can be absorbed or scattered by particles such as atoms and molecules. This can lead to phenomena such as the Tyndall effect or the spectacular colors of the sunset sky caused by Rayleigh scattering of light in the atmosphere. The implications of the speed of light and the theory of relativity. The speed of light in a vacuum, redefined by Einstein's theory of special relativity, had profound implications for physics, astronomy, and the way we understand the nature of the universe. Space-time unification. Einstein's theory of relativity introduced the concept of space-time, a unified entity in which space and time are interconnected. The speed of light plays a central role in defining this connection and how objects and events are perceived within space-time. The relativity of time. The speed of light has implications for the relativity of time. According to the theory of relativity, when objects travel close to the speed of light, their time dilates. This phenomenon has been confirmed in experiments, and global positioning satellites must take this time dilation into account in order to function accurately. Einstein and gravity. The theory of general relativity, later developed by Einstein, extended the idea of special relativity to gravity. Einstein argued that what we perceive as gravitational force is actually the result of the curvature of spacetime in the presence of mass. This theory revolutionized our understanding of gravity, energy and matter. Einstein also formulated the famous equation E equals mc squared, which shows that energy and mass are equivalent, and energy can be converted to mass and vice versa. This was applied in the development of nuclear energy and changed the paradigm regarding the relationship between matter and energy. Impact on physics and technology. The discovery that the speed of light is a universal constant changed the foundation of physics and influenced the development of technology. Modern communications, medicine, and space exploration are just a few examples of areas where this understanding has had an impact. Communications and optical technology. The speed of light in a vacuum plays an essential role in modern optical technology and communications. Optical fiber, which uses the properties of internal reflection of light, allows data to be transmitted at incredible speeds and over great distances. This technology is used in telephony, the internet, and communications networks. Medicine and medical imaging. In medicine, the speed of light and its principles are used in medical imaging, including magnetic resonance imaging and computed tomography. These technologies allow obtaining detailed images of the inside of the human body, helping to diagnose and treat conditions. Space exploration and astronomy. In astronomy, observations based on the speed of light allow us to understand astronomical distances, stellar composition, and the evolution of the universe. The concept of redshift, when light from distant objects is shifted toward the red part of the spectrum, helps us infer the expansion of the universe and study distant galaxies. Evolution and history of the universe. The speed of light can be thought of as a window into the past. For example, when we see the sun, we actually see it as it looked about 8 minutes ago, because its light has traveled to us. By studying light from distant stars, we can understand what the universe looked like at distant points in time. Fundamental research in physics. Experiments that measure the speed of light and study its properties help us better understand the nature of subatomic particles and their interactions. These studies are essential to the development of our knowledge of the microscopic universe.